You know, Einstein's field equation is the basic equation of general relativity, or you can say that the basic equation of the Einstein's theory of gravity is known as Einstein's field equation. Okay. So after a long discussion of tensor analysis and the very basic facts, from today we are going to start our first concept of general relativity, and this is regarding the fundamental equation or the basic equation of general relativity. Because you know, this general relativity theory was proposed by Einstein, and he has provided an equation to discuss the problem of gravity. So in this present lecture, our aim is to know what is this Einstein's field equation and how we can derive it. Okay? You have definitely studied Newtonian theory of gravity, which is actually a classical theory, and according to Newton's theory, you know, the two masses attract one another by an attractive force which is called force of gravitation. So in accordance with Newtonian theory, gravity manifests as an attractive force. Okay? But Einstein comes into the picture with a new idea. According to Einstein, gravity is not manifested as a force, but it is manifested as a curvature of space-time. Okay? So, how this problem of gravity can be dealt? Einstein thought about it in terms of the curvature of space-time. Okay? And you know, if we express any law in tensorial form in terms of tensor equation, then that law remains invariant under the coordinate transformation. So Einstein tried to formulate mathematically the law of gravitation in terms of a tensor equation. Actually, in different textbooks, you will find or you will get the different methods to derive the Einstein's field equation. But here in this lecture, I am presenting just a basic technique or basic method, you can say, to derive Einstein's field equation. And this will be just the starting from the Newtonian theory of gravity and how that classical law can be converted into the relativistic law of gravitation, we will see here. Okay? But before that, I would like to state what is this Einstein's field equation, okay? What is its physical meaning, and after that I will try to derive it. Just starting with the classical field equation of Newtonian theory. Okay? So first of all, you can see what is this Einstein's field equation. Actually, we express Einstein's field equation in two units in general relativity. First one is called natural units and another is called, in fact, relativistic unit. And you know, in natural unit, we take the universal constant c, which is speed of light in free space, equal to 1. So whenever you write any expression, any equation in natural unit, definitely you will have to take c equal to 1. So if you are talking about natural units, that is you take c equal to 1, then Einstein's field equation is given like this. This is g mu nu equal to 8 pi g times t mu nu. You have studied in my previous video in very detail the Ricci tensor, the Ricci curvature tensor, or you can say the Ricci curvature tensor, or Ricci scalar. And you have also learnt about Einstein tensor. So what is this G mu nu? Definitely you have recalled it. This is nothing, this is simply Einstein's tensor. Okay? And what is this T mu nu? You know, you have just studied this T mu nu just in my previous video. This is nothing, this is simply the energy momentum tensor or a stress energy tensor, you also call it. Okay? And you have learnt earlier that this Einstein tensor is a combination of the Ricci tensor and the Ricci scalar. And this G mu nu is given as R mu nu minus 1 over 2R times G mu nu, and that will be equal to 8 pi G times T mu nu. So this is Einstein's field equation expressed in natural units. Here this R mu nu is what? Definitely you can say this is a Ricci tensor, okay, or Ricci curvature tensor, or we simply say it curvature tensor. And this capital R denotes the Ricci scalar, okay. And what is this G mu nu? You know, this is fundamental tensor or metric tensor, you can say, okay. And this capital G, you know, this is the well-known universal gravitational constant in Newtonian theory, okay. So this is the Einstein's field equation written in natural units. But if you will talk, or if your aim is to write down this field equation in relativistic unit, then you know in relativistic unit the universal gravitational constant G is also taken 1. So when G will be replaced by 1, then this Einstein's field equation will be expressed in relativistic unit. Because in relativistic unit we know C and G both are equal to 1, and hence you can write this Einstein field equation in relativistic unit as G mu nu equal to 8 pi times T mu nu, G has been taken 1, or instead of G mu nu again you can write R mu nu minus 1 over 2 G mu nu times R. And I have written here the meaning of all the quantity just I have told you. You have seen that this G mu nu is Einstein tensor, R mu nu Ricci curvature tensor, this capital R is Ricci scalar. And what is this Ricci scalar? You have learnt that when we take the trace of Ricci tensor, or when you actually contract the Ricci tensor, then you obtain a scalar which is called Ricci scalar, okay. And G mu nu, as I have told you, this is metric tensor of space-time, and T mu nu is energy momentum tensor, and G is Newton's gravitational constant, okay. Now actually what this Einstein equation physically state, you can see in LHS there is a tensor R mu nu minus 1 over T G mu nu R. In fact, this R mu nu represents the curvature of the space-time, okay. 8 pi or 8 pi G is a constant factor, and this T mu nu is the energy momentum tensor. It means the curvature of space-time is equal to some constant times the energy momentum tensor. It means you can also say that curvature of a space-time is proportional to the energy momentum tensor. So a space-time curvature is equal to constant times energy momentum tensor. Physically, the Einstein's field equation states that, okay. And actually, what physical ideas we obtain from this Einstein field equation? So what are the physical motivations? In fact, when you derive this Einstein field equation, you have to think or you have to consider some basic facts. First of all, we must think about general covariance principle. In fact, while deriving this or while providing this field equation, Einstein's aim was the consideration of general covariance. It means the laws of physics are valid in any coordinate system. So Einstein provided an equation in such a form which will be valid, which will hold in all coordinate systems. And you know, tensor equation is valid in all coordinate systems. So Einstein thought that the field equation for the gravitation must be in tensor form. Okay? Again, as Newton's theory of gravitation is a classical theory, and Einstein has provided the relativistic theory of gravitation. So definitely in the limit of, in classical limit, this Einstein field equation or Einstein theory of gravity must be transformed into Newtonian theory of gravity. So while deriving this equation, Einstein thought that the form of equation should be such that whenever we will impose the condition of classical limit, that equation must be converted into Newtonian theory of gravity. Okay? So this was also a physical motivation for Einstein. I have written here in short, reduced to Newton's gravity when speeds are slow and gravity is weak. If you talk about the slow speed, that is the small speed, and weak gravity, then this Einstein's relativistic theory must be transformed into Newtonian theory of gravity. Okay? And another motivation behind this well-known law of physics was conservation of energy and momentum. You know, the material tensor T mu nu, this actually is the parameter in terms of which we can express the conservation law of energy momentum. You know, the covariant derivative of T mu nu is equal to 0. So you write the covariant derivative in this manner: del nu operated on T mu nu equal to 0, or we write it in the comma symbol like this: T mu nu semicolon nu, that is equal to 0. Actually, the covariant derivative of material tensor or energy momentum tensor is 0. This actually implies that energy and momentum remains conserved. So these three facts was the physical motivation behind the derivation or behind the proposal of this field equation to Einstein. Okay? So what is Einstein's field equation? What was the physical motivation? What physically it means? You have learned. And definitely you should remember the expression, this field equation, you should remember it. Now we are going to see how we can derive this Einstein's field equation. EFE I have written for Einstein's field equation. Okay? As I have told you, in different texts you will get the different mathematical approach to derive this equation. But here I am talking about the most elementary and most basic method. Starting from Newton's theory of gravitation, we will transform the classical equation into the relativistic equation. As if you have learnt in quantum mechanics Schrödinger equation, then you have seen that Schrödinger equation, which is a quantum mechanical equation for matter wave, that is derived from the classical wave equation. Just like that, we will derive the relativistic field equation of Einstein for gravitation, starting from the Newtonian classical theory of gravitation. You know, when we apply Newton's theory of gravitation, then the field equation in the presence of matter is written by Poisson's equation. Okay? So, according to Newton's theory of gravitation, the field equation in presence of matter, which is actually called Poisson's equation, is given by this expression. Laplacian phi equal to 4 pi 0. Here you know this del square operator is called Laplacian operator, which is actually a second order partial differential operator. And phi, this is actually gravitational potential. G is universal gravitational constant, or you can say the Newton's gravitational constant. And rho is material density. Okay? So this is a classical equation, and it expresses Newton's theory of gravitation. And this very equation is called Poisson's equation. Okay? Now, as I have told you, our aim is to write or to derive Einstein's field equation utilizing this classical result. But how? As I have told you that behind the for deriving this equation, there was some motivation to Einstein. Einstein's first motivation was the principle of general covariance must be valid. So the equation for gravitational field must be in terms of tensors or in tensorial form. So the quantities existing in this equation 1, which is classical equation for gravitation, we must think about the equivalent tensorial quantity. And in this regard, you know, when you have studied the fundamental tensor, then you have seen in a non-relativistic limit, it means when you talk about a speed which is much smaller than the speed of light, then this fourth component of the fundamental tensor G44, this quantity plays the same role as played by the gravitational potential phi. It means phi is just equivalent to the fundamental tensor. Okay? So if your aim is to transform this classical law into a relativistic law, you must replace this gravitational potential phi by the fundamental tensor G mu nu, because this G mu nu becomes phi when we impose the non-relativistic condition on it. Okay? Therefore, the LHS of this equation 1 must be expressed in terms of the second order derivative of this fundamental tensor G mu nu. Definitely. Okay? Because here Laplacian is operated on phi, which is a second order partial differential operator. So definitely the LHS of this equation must be expressed as a second order partial derivative of this fundamental tensor G mu nu. But how we can write such a term? Again, you know, this material density rho you have just seen in the my previous video, that this rho is one of the components of energy momentum tensor T mu nu. Just you have seen. Okay? And as rho is one of the components of energy momentum tensor T mu nu, therefore in relativistic theory of gravitation, RHS of this equation, RHS of this equation must be must be replaced by the material energy tensor T mu nu. This rho must be replaced by T mu nu. So I have mentioned it here that therefore in relativistic theory of gravitation, RHS of equation must be in terms of T mu nu in such a way that its divergence vanishes. You know, divergence of T mu nu is equal to 0. Okay. Now, if the classical equation defined in 1 is to be generalized to the relativistic theory of gravitation, then this equation must be expressed as a tensor equation, as I have told you earlier, satisfying the following conditions. When these three conditions will be satisfied by the tensor equation, then that will be a valid equation, or that will be a valid equation for dealing the relativistic theory of gravitation. So what is the first condition? The first condition is that tensor equation should not contain the derivative of g mu nu higher than second order, because you know in the classical equation there is a second order derivative of the gravitational potential phi, and phi will be replaced by g mu nu. So definitely you cannot take the higher order derivative of g mu nu, which is actually higher than 2. So definitely we should take this condition under account for writing that equation. Again, this equation must be linear in second differential coefficient. Okay. And third one is its covariant divergence must vanish identically, because the covariant divergence of T mu nu is 0. So if you will replace rho by T mu nu, then this fact must hold. So when you will take actually all these conditions under account, okay, then you have seen in my previous video when I have discussed the fundamental tensor that the covariant derivative of this g mu nu is identically 0, and the only tensor which involves this g mu nu up to second order is one obtained by contracting once and twice the curvature tensor. Okay, only that tensor. So I have mentioned it here. We know that the covariant derivative of g mu nu are identically 0, that it means this much is 0. And the only tensor which involves g mu nu up to second order is one obtained by contracting once and twice the curvature tensor, this R. Actually, if you will contract this curvature tensor, and you have already learned these things, after first contraction, this curvature tensor is transformed into Ricci tensor. Okay, and we take the trace of the Ricci tensor, then that is converted into what? That is converted into Ricci scalar curvature. Okay, scalar curvature. So, and Einstein tensor is a combination of the Ricci tensor and this Ricci curvature scalar. So definitely the tensor which will fulfill all the criteria which I have mentioned above, that is contained in this Einstein tensor. Okay, because we also know that the divergence of Einstein tensor is 0. We have already learned. If you have not watched my video on Einstein tensor, Ricci tensor, I will suggest you go through all those videos first of all, and after that you will watch the video on Einstein's field equation, then the every concept will be clear to you. Okay. So Einstein's tensor G mu nu, which is defined like this, satisfies all those criteria, and therefore Einstein suggested that in Poisson's equation this del square phi must be replaced by Einstein's tensor. Must be replaced by Einstein's tensor. Okay? And that Einstein's tensor must be proportional to rho. And you know the relativistic equivalent of rho is what? This is material tensor T mu nu. Okay? So this is Einstein's tensor, and this is proportional to T mu nu, and K is the proportionality constant. Okay? So equation 1 is now written like this: R mu nu minus half G mu nu times R equal to K times T mu nu. Here actually this constant K is also known as Einstein's constant, and this constant K is related to this G. Okay? If Einstein's relativistic theory corresponds to Newton's theory in non-relativistic theory, it means if it is possible that in non-relativistic limit Einstein theory will be transformed into Newtonian theory, then you can say that this Einstein constant K must be related to this Newtonian constant G. Okay? And as I have told you earlier, that in natural unit we take C equal to 1, but G is taken at each. And it is seen that in natural unit the value of this K is equal to 8 pi G. But if you will use a relativistic unit, then you have to take G equal to 1 too, and then we simply say that K is equal to 8 pi. So if now we will write the Einstein field equation. After substituting this value of K, the Einstein field equation will be R mu nu minus 1 over 2 G mu nu R equal to 8 pi G times T mu nu. Okay? Or instead of this, you can write Einstein tensor G mu nu. Okay? This equation has been written in natural unit. But when you will write the same equation in relativistic unit, then you must take G equal to 1, and the Einstein field equation will be G mu nu equal to 8 pi times T mu nu. Okay? So you can see how easily we can derive this Einstein's field equation starting from the Poisson equation for Newtonian theory of gravitation. Okay? So this equation, you have seen that since here material energy tensor is present, it means this equation has been derived in the presence of matter. So this very equation represents the Einstein's law of gravitation for naturally curved material world. Okay. Now you can see Einstein's this equation has been written in terms of the covariant tensors, but we can write this Einstein field equation in terms of contravariant tensors, in terms of mixed tensors too. And for this you can simply raise the indices. You can see when we raise this index mu, then this will be R mu nu, and in each term mu will be raised, and Einstein's field equation will become like this. This R superscript mu subscript nu minus this much is equal to this much. Here mu has been raised, or you can say that this G mu nu is equal to this much. And if nu is also raised, then R mu nu, this is a second order contravariant tensor, minus this much equal to this much. So Einstein's field equation may be written either in terms of the covariant tensors, okay, or mixed tensors or contravariant tensors. All are equivalent to one another. Now let us see. This is our Einstein's field equation. And now we are going to see what will be actually Einstein's field equation in free space, in empty space, where there is no matter. What will be Einstein's field equation? Okay? And for getting this equation, let us multiply this Einstein's field equation both sides by this fundamental tensor G mu nu. Okay? So let us take multiplication by this. So this will be G mu nu times R mu nu minus 1 over 2 G mu nu times G mu nu. Okay? And this is equal to 8 pi G times this much. Okay? Now you know this product of this R mu nu with this G mu nu will give us simply R. This is a scalar. This is a scalar. Okay? And here the product of these two fundamental tensors, this is in fact equal to delta 1 1. Okay? And this will be equal to, according to Einstein's summation here, delta II you can say, this will be 1 plus 1 plus 1 plus 1. Here there is no sign of summation, but according to Einstein's summation convention, there will be a sum of 4 terms. And this will be equal to 4. So this product is equal to 4. So this is simply 4 by 2 times R. Okay? And again here this product will be simply T, but this is material energy tensor. Okay? And R minus 4 by 2R, it means R minus 2R, that is minus R. So you can write R equal to this much. But if you talk about empty space, vacuum, free space, where there is no matter, then in absence of matter, you know, this material energy tensor will be 0. No stress will be developed, no energy momentum tensor will vanish. And T mu nu is 0, that implies that this T will be also 0. And if T is 0, then this Ricci scalar is also equal to 0. So in case of empty space, this Ricci scalar is 0 and the energy momentum tensor T mu nu is also 0. So if your aim is to write down Einstein's field equation in absence of matter or in empty space, then what you will do? You must take this T mu nu equal to 0 and this R also equal to 0. And therefore, Einstein's field equation in empty space will become R mu nu is equal to 0. So actually this Ricci curvature tensor is equal to 0. This is Einstein's field equation in empty space. It means if the space is empty, there is no matter, then the space will be flat, not curved, because here curvature tensor is 0. It means the empty, if the universe is empty, there is no matter, then definitely our space-time will be flat. Okay? So this is all about the Einstein's field equation, derivation of it. But in our forthcoming lecture, we will discuss this Einstein field equation, we will see its solution, we will see something more regarding this. Okay? So I think all the concept which I have discussed in this lecture has been definitely clear to you. Thank you very much.